Hi guys, welcome to 9.2, Explaining Energy Changes. Now if you are a core student, you just switch this video off. There is nothing in here that will come up on your exam. If you are an extended student, you are going to take the extending paper, then carry on watching because all of this is relevant to you. So what do you need to do? For the extending curriculum, it's no good just explaining whether a reaction is exo or endothermic and looking at the basic energy diagrams. You have to be able to use this term called bond energy to do some calculations and explain why a reaction is exo or endothermic. Bond energy is just the amount of energy that is trapped as chemical energy in the bonds that hold together the atoms. So it's nothing too complicated. And then all you have to do is do a very, very simple sum to work out the energy change from the start of the reaction, or the amount of energy, the total bond energy that is locked up in the reactants, to the amount of energy or bond energy at the end of a reaction, or the amount of energy in the products. And then that will allow you to decide whether it's an exothermic or an endothermic reaction. Please don't worry, you will never have to remember bond energies. They will always give you the bond energy, always give you the bond energy in the exam. So pause the video now and see if you can fill in the blanks. Okay, so hopefully you've paused the video, you've had a little think, you've got your brains warmed up. Here's the answers. If you have an exothermic reaction, then the surroundings must get hotter because it's exothermic. Therefore, the energy stored in the bonds, or the bond energies, the total bond energies in the chemical system, must have got lower throughout the course of the reaction. Therefore, this new thing here, delta H means the change in energy. The change in energy between the reactants and the products must be negative, because your products have less energy in them than they started with. That's evident in the fact that your surroundings have got hotter. In contrast to that, in an endothermic reaction, the surroundings get colder, we know that. Therefore, if we're talking about the chemical system, we're talking about the amount of energy trapped in the bonds, it must have got higher. As the reaction has proceeded, it must have got higher, because energy has been drawn from the surroundings and is now locked up in those chemical bonds. Therefore, the delta H, or the change in energy, must be positive. So why is that? We need to be able to talk about making bonds and breaking bonds. At the beginning of a reaction, we are breaking bonds apart. If you imagine that those bonds are stuck together in the reactants, what we want to do is we want to break them apart, rearrange them, and put them back in a different way as something else. That's what a chemical reaction is. So in the beginning, we have to break bonds. Now, to break bonds, we need to put energy in. Imagine if I told you to break a chair or break anything, you would have to put energy in to break whatever it was you were breaking. Well, the same can be said for the bonds between atoms. We have to put energy in to break them apart. That happens at the start of a reaction. Then as the reaction progresses, as you make products, you begin to make new bonds. And when you make new bonds, when you go from broken bonds to complete bonds, that gives energy out to the system. Now, if we remember those fundamental rules, it's actually very easy to go on and do the next part of the lesson. Let's take this, for example. Let's take this chemical reaction. 1 mole of hydrogen gas plus 1 mole of chlorine gas makes 2 moles of hydrochloric acid. Now, bond energies are always given in kilojoules per 1 mole. So never be fooled to thinking that it's the total amount of energy that you've been given. You must always use the big numbers in the equation to work out the number of moles that you have. So The reason why I've done the arrows in red and blue is because if you think at the start of the reaction here, we need to put energy in to break these apart, to break the hydrogen apart, to break the chlorine apart. So we're putting energy in. That is an endothermic process. We have to get that energy from the surroundings. We can't just make energy, can't be created nor destroyed. We must put those in from the surroundings. At the end of the reaction, we are making new bonds. We are taking those broken apart hydrogens and chlorines and we are forming them together as hydrogen chloride. So that's an exothermic process. It's giving energy to the surroundings. Let's have a look which is greater, because that will tell us whether this is an exothermic reaction in the forward direction or an endothermic. To break 1 mole of hydrogen apart takes 436 kilojoules. So that we could say the bond energy is 436 kilojoules per 1 mole. To break chlorine apart, the bond energy is 242 kilojoules per 1 mole. Now we only have 1 mole and 1 mole. So that's all we need. We've got the right amount of bond energies there. No sum required. Over here, to make this hydrogen chloride, when we make them, we give out to the surroundings 431 kilojoules for every 1 mole that we have. Well, we know, don't we, that we don't make 1 mole, we make 2 moles. So we're going to have to times this by 2 later on in our calculation. So let's do the calculation. 436 plus 242 equals 678 kilojoules in total that we've had to put in to break that hydrogen and chlorine apart. When we've made the hydrogen chloride, the amount of energy we've got out is 431 times 2 moles, because we've made 2 moles. So we've given out 862 kilojoules in total. So all we have to do now is do, well, how much energy did we put in, take away or minus how much energy we got out. And that will tell us that actually we have minus 184 kilojoules. In other words, there's 184 kilojoules less in the system. And if there's 184 kilojoules less in the system, then the reaction must be exothermic, because we've put less energy in, only 678 kilojoules, and we've got more energy out. So if we're getting more energy out, then in our surroundings are getting hotter. Therefore, our reaction is exothermic. And if our surroundings are getting hotter, that is because our chemical system has less energy overall, because it's given it away to the surroundings. So you'll see all exothermic reactions have a minus delta H, or a minus change in energy, because the system gets less energy. If we have a look at the energy level diagram here, you can see that the reactants here, they had more energy in them than the products. And we can see that, can't we? They had more energy in them to begin with than the products. So the products have got less energy. Therefore, we've put this energy in to reach the activation energy. The bonds were broken. We made all this energy given out. Overall, we've lost 184 kilojoules, or we've given 184 kilojoules to the surroundings. Let's have a look at this one. This is ammonia making nitrogen and hydrogen. It's the thermal decomposition of ammonia. You can see this equation is telling us there's 2 moles of ammonia to make 1 mole of nitrogen and 3 moles of hydrogen. Let's have a look at the bond energies. To break a nitrogen-hydrogen bond is 391. Well, we've got 3 of those, haven't we? Because we've got nitrogen joined to a hydrogen, hydrogen, hydrogen. So we've got 3 hydrogens joined to 1 nitrogen. So we need to break these 3 bonds apart. To break each one, we must put in 391 kilojoules. Now we've got 2 moles of that. So actually we've got 6 nitrogen-hydrogen bonds overall, or 391 times 2. Okay, that gives us 2,346 kilojoules that we must put in to break these 2 moles of ammonia. On the other side, we've got a triple nitrogen-nitrogen bond, which for every 1 mole is 946 kilojoules that you're going to give out when you make that nitrogen. It takes 436 kilojoules of energy for the hydrogen-hydrogen bond, and we've got 3 of them. We've got 3 moles of hydrogen-hydrogen bonds here, so we have to times it by 3. So as you can see, we've got 946 kilojoules, plus the 3 moles at 436 each. That gives us 2,254 kilojoules that are made. So already you can see that we are giving out less energy than we are putting in, but we'll do the sum anyway. We put in 2,346. We give out 2,254. Therefore, we have a positive change. In other words, our chemical system has 92 more joules in it than we had originally. You can see we've given out less than we've put in. So if we've given out less, our chemical system must have gained, or we've got a positive delta H. Our chemical system has 92 more kilojoules in it than it had at the beginning. If we have a look at that in an energy level diagram, we can see that here is our reactants, here is our ammonia. We put in some energy, those bonds are broken, that energy has come out, but hang on, we've given out less energy than we actually put in. We have to put in 92 kilojoules into the system in order to promote the products up here. So you can see that this is your classic from last lesson. This is your classic endothermic reaction energy diagram. And what we've done is we've just used some numbers to quantify those energy changes. So that's it for explaining about energy level diagrams. What I want you to do is to go back to your booklets now and do the calculations. The answers to the calculations are here. So don't look at them just yet. Pause the video now, do those energy level calculations, and then I will display these at the end of the video. So pause the video now and do your calculations. Pause it. Okay, now you've paused it, you've done your calculations, check them off, see if you were correct. You'll have to pause the video again because I'm going to stop it now. Okay, right, I'll see you in 9.3. If you've got any questions, don't forget to come and see me. Okay?